Welcome to this NPTEL lecture on techniques and principles of modern radar system. So, we were discussing MTI filter performance matrices. So, in the previous lecture we have seen the clutter attenuation, the first metric, but we have told that time that actually we need to see that attenuation with respect to the level of the signal. So, something like signal to clutter ratio at the input and output should be compared, that is the MTI improvement factor. So, I is the symbol of MTI improvement factor, it is SCR at the output of whom, obviously this is the MTI filter, so the SCR here, this is the input and this is the output. So, SCR at the input by SCR at the input. So, that means I can write S naught by C naught, where S is the signal power at the output, C we have already said clutter power, divided by Si by Ci. So, this I can write that the signal power ratio at the output by input into the clutter attenuation what we have already seen. So, then what is S O by Si? So, this I can say that average, from here I can write that average power gain of MTI filter, and this is the clutter attenuation. So, we know if the transfer function is HF, so this can be written as that H omega square, but there should be average. Why? Because at all the frequencies it may not be same. So, we will have to take some averaging and give that. Now, for if I want to calculate this for a single DLC, again we specialized the SDLC. So, we know this CA we have already found. So, I can put that value FR by 2 pi sigma F square. Now, we will have to evaluate this one. So, we know that in a pulsed MTI radar, the H omega or HF, it is periodic with period FR. So, this thing will turn out to be that 1 by, so we know that I can write that HF is periodic with period FR. This is for a pulsed radar, we have seen that pulsed radar. So, this I can what will be the this average thing that I can find out. So, let me separately do it, that H f square average, that will be 1 by f r minus f r by 2 to plus f r by 2, and then for a single DLC I know that expression sin square pi f by f r df. So, this is the average. If you do that, this whole thing, it can be easily done, sin square integration you can do, the answer will be 2. So, we can find the, for a MTI improvement factor for a single DLC implementation, it will be 2 into f r by 2 pi sigma f whole square. This is a very useful relation, that it is this something like clutter attenuation, but multiplied by 2 for single DLC. And also I am again reminding the region of validity, that sigma f should be less than f r, then only this is valid, because we have assumed that in evaluating that. So, let us take an example, that suppose a certain pulse radar has a PRF (800 Hz), and suppose the clutter RMS spread, that sigma f is 6.4 Hz, a very typical value. So, what will be the MTI improvement factor? For this we can calculate what is first CA, clutter attenuation, that f r value we know 800 Hz. So, this expression basically, that if we do that, put it, sigma f is given, this is given, this will turn out to be in dB scale 25.97 dB, and this factor of 2 will give a 3 dB. So, MTI improvement factor for this will be almost 29 dB. So, you see that the MTI filter is giving a 29 dB thing, very good gain, even a single DLC, and actually you can now calculate that instead of single DLC, if I give a double DLC, etc., what will So, for I can write that for n pulse, 2 pulse, 3 pulse, that n pulse MTI filter, if you do that evaluation, the improvement factor is given by a general formula 1 by, people have derived it, I have not gone into that, but you, if you know this, you can find what is the improvement factor. Where you see it is a double factorial notation I have given, I will explain that. But what is q square? So, q square is 1 by sigma I is equal to 1 to n AI square, and AI is nothing but the binomial coefficient of the MTI filter. Now, this thing, see what are these? Actually, MTI filter, we have seen that higher order things we can always implement them by a transversal filter, and there are weights. Those weights are the coefficients, and it can be shown that they are nothing but binomial coefficient. If we choose it that way, then that gives you the optimal thing. We will discuss that. So, AI is that, and what is these double factorial things, that a odd double factorial is 1 into 3 into 5 into 7 up to 2n minus 1, and an even double factorial is 2 into 4 into 6 into up to 2n. So, we can now find out from that formula that for a 2 pulse MTI, 2 pulse MTI filter, what will be Q square? Q square will be, you can find out because you have those coefficients. So, it will come out to be half. For a 3 pulse MTI filter, Q square will be 1 by 6. This you can easily check. For a 4 pulse MTI filter, Q square is 1 by 20, and so you can easily write that what is I, that means MTI factor for 2 pulse, that we have already seen this, but from this formula again you can check, this will be 2 FR by 2 pi sigma f whole square. Now, what is the corresponding thing for 3 pulse? I 3 pulse will be 2 FR by 2 pi sigma f whole to the power 4, and I 4 pulse, that will be 4 by 3 FR by 2 pi sigma f whole to the power 6. So, you see that if we have more pulses we process, then the improvement factor goes with a square ratio. That means, for a 2 pulse it is FR square, for a 3 pulse it is FR whole to the power 4, and remember that FR divided by sigma f, that is a very huge number. So, you are getting a huge improvement in a thing. Now, actually subcluster visibility, you just, I will qualitatively say, because we have not seen certain thing. It is actually when a radar makes a processing, it is with a given constants, those are called probability of detection and false alarm, etc. That we have not discussed yet, but subcluster visibility is this thing, but how much under those given parameters, what is the performance matrix. So, I will describe it, that subcluster visibility, it is describes the radar's ability to detect non-stationary targets embedded in a strong clutter background for a given probability of detection and false alarm. So, for a given constant, how much it can see targets embedded in a strong clutter background. So, for example, a radar with 10 dB SCV will be able to detect moving targets whose echoes are 10 times smaller than those of clutter. So, we have seen that sometimes the RCS of the clutter may be 60-70 dB higher than the RCS of the target. So, subclutter visibility is an indication that whether the thing will be able to detect or not. So, I am just writing SCV is defined as the moving target indicator by the signal to clutter ratio of the output for a given probability of detection. So, you see it is I, but under that minimum MTI output signal to clutter ratio required for proper detection for a given thing. So, for your later you will understand this meaning. Actually, it is the numerator is MTI improvement factor, but denominator is the minimum MTI output SCR required for proper detection for a given probability of detection. As I said that it is scaled by that what is the minimum SCR that requires, you are scaling by that. So, that gives you the subclutter, how much clutter thing you can process. Now, a few things about the implementation. So, we have seen the performance matrices, how to calculate that. We have got a formula also, by that you can find for various stages of MTI filter what will be the thing. Now, I will say that if we recall the FIR, the implementation of delay line canceller DLCs. So, we can say that basically if the input is coming, what the A is doing, that it is first giving some weights, then there is a delay, I will write T, then there is another weight, then further delay, there is another weight, then delay. So, I will give this. Further weight like this. So, if this is the last one, I can call that if there is a n stage tap delay thing, then the final thing will be n plus 1. So, I will say there are something, and all these are summed. So, there is a summer with which all these are connected. So, finally, all these are put here. So, this is a summing network and you get the output from here. So, this is the block diagram of a n stage tapped delay line MTI filter. This we already have seen. Now, what people have shown that if these weights, how to choose these weights W1, W2, W3, W4. Now, you have 2-3 cases we have seen, and that time we have not recognized, but actually you will see that the way we have got those values, they are nothing but their binomial coefficients of 1 by x whole to the power n. In our case, actually this W1, W2, W3 etcetera, they are nothing but the binomial coefficients, that means the coefficient of the expansion 1 minus x whole to the power, sorry, this will be capital N, with alternating signs. So, I can say that the W's are binomial coefficients of the expansion with alternating signs. That turned out, and this is nothing but our this what we have said, that n stage cascaded single DLCs. So, that means we know the binomial coefficients. So, I can write that what is says that Wi is minus 1 whole to the power I minus 1, this will make this alternating, and n factorial by n minus I plus 1 factorial into I minus 1 factorial, where I is equal to 1 to n plus 1. Okay. So, that means you can always do that. So, in you can check, suppose for if you take capital N is 4. So, basically n stage that thing. So, what will be W1, what will be W2, and you can see that in your actual thing you can also do that. So, let us say that because up to 3 we have done. So, let us do for 4 also, that n is equal to 4. Then if you find from here what will be W1, if you put it, you will see that W1 will be 1, W2 that will be minus 4, W3 that will be 6, W4 that will be minus 4, and W5 that will be 1. And so, that means the thing will be, you are giving an input, then you are giving a weight of 1, then you are putting a delay, you are giving a weight of minus 4, then you are giving another delay, you are giving a weight of 6, then you are giving another delay, you are giving a weight of minus 4, then you are giving the another delay and giving a weight of 1. All these you are summing. So, there is a summer and you are getting the output. So, if this is x t, you are getting y t. Now, this is from binomial thing, and from your 4 pulse I can see that if you have x t you are giving. So, a delay you are getting, here you are putting some. So, this is one stage, then there will be another stage, then there will be another stage, and then there will be the 4th stage. So, this output is y t. So, 4 cascaded single DLC. So, you can write the expression, if I call this as y 1 t, this one y 2 t, this is y 3 t, final one is y t. So, you can write it that what will be the final one, that means y t will be y 3 t, sorry, y 3 t minus, this is t, this is minus y 3 t minus t, then y 3 t will be y 2 t minus y 2 t minus t, and y 2 t will be y 1 t minus y 1 t minus t, and y 1 t is x t minus x t minus t. So, you can put this one by one here, and finally, we will see that you can write y t as x t minus 4 x t minus t plus 6 x t minus 2 t minus 4 x t minus 3 t plus x t minus 4 t. So, you can check these weights are nothing but the binomial filter. Now, this binomial coefficient choice, that means this implementation, this is optimal. This is optimal in the sense that it maximizes. So, this is optimal in the sense that it maximizes the MTI improvement factor I. Also, it maximizes the probability of detection. So, if we choose it in this way, people have proved that, because you can have other implementations also, 4 stage etc., but this is the best in the sense of this, it maximizes the MTI improvement factor and also it maximizes the probability of detection. So, maximizes I and maximizes PD, probability of detection. This we will see later in the detection theory what does it mean. Now, we write it, but it does not guarantee. So, these two things is very useful, but it does not guarantee. I will say that this does not guarantee two things: a deep notch at DC, that means that notch at DC does not get guaranteed by this. For that, you will have to find various things, and also the flat passband response in MTI. So, this is a open problem, that determination of Wi, so that apart from improving I and PD, these two A and B, these two also is achieved. One answer to that we have seen is the recursive filter, but still there are other things, that how to choose those values so that we can get a good A. So, this is a still evolving research area, that how to choose this. And okay. So, I think we close this lecture here. Some more things about this MTI filtering, because this is a very important research area, and with the technology, this is much focus is there on radar researchers. They concentrate here that how to improve this MTI detection, etc. So, we will discuss something more, and that how to determine that which stage, how many stages of DLC will take, that thing we will discuss in the next class. Thank you.